Alrighty guys, so today we're going to be going over, make this a little bit bigger. We're going to go over energy. Okay. So every change that occurs, large or small, involves energy. Just sitting in your chair reading and breathing involves the use of energy. Energy is stored in different forms such as food, gasoline, etc. So if you try to just sit in your chair and not move, not to move, you're still using energy. I mean, you're breathing, your heart's beating, and all that stuff. You're thinking. So just standing still doesn't mean you're not using energy. You're using a little bit less energy because you're not doing other things like moving around, but nevertheless you're using energy, right? And energy can be stored in different things, right? So gasoline, you put a match to gasoline, that you're going to get a huge amount of energy that comes out of it. We get our energy from food. So depending on the calories that food has, the more calories it has, the more energy it has stored in there. And there's just a certain amount of energy that the body needs, where if it's excess amount of energy, extra calories, then your body will actually store it as fat, right? So that's all of that is energy. So yes, all the fat and stuff, all that Big Mac that you ate and stuff, and if you kind of overdo it, then you're gonna have a lot of stored energy, right? So kinetic energy is what we're going to cover today. So kinetic energy is energy in the form of motion, such as running, a football passing through a goalpost, and so on. So if an object is moving, it can be anything. It can be like a bird that's flying. It has kinetic energy. It could be you walking. You have kinetic energy, but if you start running, you're going to have more kinetic energy. Okay, so anything can have kinetic energy. It doesn't have to be alive. It could be, like I said, a football, a baseball that you're throwing, and that's kinetic energy. Okay, so on the right side of your notes, you're going to copy down the formula. Ke equals mv squared over 2, and the units for mass are kilograms. Okay, and for velocity, we know that those are meters per second. So the units for joules, the units for kinetic energy are joules, Joules, or J. And this is after this dude that came up with the formula, okay? So you come up with a cool formula, you get to put your, if you want, you get to, use your last name in a unit, which is kind of cool because, their name will last forever. So we're going to be using these formulas forever to be able to help us understand the world around us. So on the left side here, we have our first example. What is the kinetic energy for a 2 kilogram object moving at 5 meters per second? So here we have 2 kilograms. Okay, so 2 kilograms is the mass. So that goes right there. Let's set up our stuff here. So here we have 5 meters per second, which is our velocity. We know a meters per second is a velocity. That goes right there. So now we're going to solve this, right? So 2 times 5 squared divided by 2. So 5 squared is 25. 2 times 25 is 50. Divided by 2 is 25. Right? And what I'm going to do is, give me 1 second. Okay, I am still recording. I went over this entire lesson, and for some reason, when I hit record, it didn't record. So this is part 2 of the lesson. You guys totally missed it. I gave you the answers to all the tests and all that stuff in that last video. I'm not going to go over that again. I'm just kidding. I didn't give you the answers. But that would have been funny though, right? Okay, so left side, number 2. And at any point, you can always, pause the video to copy down the problem. But I'm going to kind of just move on. Okay, so here we have 1,000 joules. Okay, so if we look back here, joules is KE. Okay, so this 1,000 goes right here. The mass, this is mass, right? Kilograms is a mass. And we have V squared over 2. So we're going to solve for V by cross multiplying. So 1,000 times 2 is 2,000, 20 V squared. So we want to solve for V by dividing. That cancels. And I'm left with 2,000 divided by 20 is 100. And to get rid of the squared, we do the square root, which is 10. So my velocity is 10 meters per second. Okay? Let's move on to number 3. So here we have the KE of an object is 1,500 joules and has a velocity of 3 meters per second. What is its mass? So here we have a J. So does that go in KE, M, or V? Can only go in one of these two, right? So here, let's set up the problem. That has to be there, right? The squared and the 2. That's not going away. So 1,500 will go in KE. Plug that in right there. And this is our velocity. How do I know it's our velocity? Because it says meters per second. So that gets plugged in V. So that means we're solving for M, right? And it's asking for M. But they also don't give us kilograms, so we know we're solving for M. So we're going to cross multiply here. 1,500 times 2 is 3,000. 3 squared is 9. And when I divide both sides by 9, I get 3,000 divided by 9, which gives me the 3.333333 forever 3 answer. Okay, there we go. That's kinetic energy. Okay, I'm going to move on to the next section. On a new section in your notes on the right side, you're going to copy down potential energy. Okay, so potential energy is stored energy due to its position. So this means that wherever you have the object, if you're holding it in, let's say, 5 feet off the ground as compared to 10 feet, and if you were standing right below that object, where is it going to hurt the most? If it falls at 5 feet off the ground or at 10 feet, right? So just think of that as kind of potential energy. There's different types of potential energies. So like I was going back with food, we get our energy from food, so there's potential energy stored in there. But we're going to go over the science physics part of potential energy, which is the formula here. Okay, an object doesn't need to be involved in motion to have energy. So we went over kinetic energy, energy that's moving, but if it's just standing there, it has potential energy, right? In this case, depending on the mass, gravity, which is always there, and the height, depending on how high up you are holding that object, it's going to have more potential energy. Okay, so again, picture that. Where is, if somebody was going to drop a baseball, I don't know, on your head, and it was, let's say you're lying down on the floor and they're holding it 5 feet off the ground, where is it going to hurt the most? At 5 feet or at 10 feet? So obviously at 10 feet. If you replace the baseball with a bowling ball, okay, obviously it's going to hurt more because the mass, okay, is affecting it. So these are the three things that can affect it. Okay, so here is our first 2 examples. So at this point we can, like I said, pause the video to copy these down. And I'm going to just kind of go into it. So an apple with a mass of 2 kilograms will keep stored energy due to its height above the ground. If it falls 2 meters, that stored energy is converted to energy in motion. Find its potential energy. So we know that this is a mass, goes right there. And we know this is a height, meters. The G is always gonna, it's always gonna be 9.8, so that should kind of be a no-brainer. So our potential energy here is 39.2 joules. Now we're gonna make sense out of all these numbers in a different lesson, okay? As of right now, I'm just showing you how to plug in the numbers, and some of these numbers, I think I just made up some of these numbers. So, I mean, a 2 kilogram apple, that's gotta be a huge apple, you know, or a really heavy apple. But yeah, I just made these numbers up just to show you where to plug in the numbers, okay? So here, let's do number 2. A 0.06 kilogram tennis ball starts to fall from a height of 2.9 meters. How much potential energy does it have? So we know that we can automatically plug in 9.8 here, right, for gravity. And it looks like they're giving us a mass, and they're giving us a height. So if they give you, should be a 2. If they give you these three numbers, 0.06 times 9.8 times 2.9, we just multiply them, and that will give us our potential energy, which is 1.7 joules. Now I want you guys to notice that in these two examples, they gave us a mass, gravity, and height, and you multiply all three. Now I'm going to just make up some numbers here. What if they gave you potential energy and they said, oh, the potential energy is 5 and the mass is 2 and we know gravity is 9.8. Find H. Solve for H. So how would you do that problem? Well, don't let it throw you off. Okay, you do the same thing. 2 times 9.8. 2 times 9.8 gives me 19.6. And then if we wanted to solve for H, we would just divide, right? And I can already tell we're going to get a decimal because the bottom is bigger than the top. Anytime that happens, you get a decimal, right? So 5 divided by 19.6 gives me 0.25, for example. 0.25 meters, right? It would be the same thing if you were solving for m, right? So if you had something like this and it was like m 9.8 times, let's say they gave you a height of 3. You would do the same thing, okay? You would multiply these two and then you would solve for m, okay? So don't let this throw you on these type of problems, okay? Just plug in the numbers where they go. Okay, and then we're gonna move on to okay, so work in power. So you're gonna copy this on the right side of your notes. And when, let's say you press your hand on the desk, you press it on the desk as hard as you can, and you try to hold it there, you try to put as much force as you can. After a while, you're probably gonna get tired, right? After so much time passes, your muscles are gonna get tired, you're gonna get tired, and guess what? Even though it seems like you're putting a lot of effort into pushing your hand on the table, you're actually considered not to be doing any work. But how can that be, right? You're clearly doing work. You're clearly putting your hand on your desk and you're pushing down as hard as you can for, let's say, 5 minutes. And yeah, your muscles are gonna start hurting and so on, and you're gonna get tired. But people think that pushing or pulling something is, they think that work is being done. However, the scientific meaning is more specific. In order for you to do work in the science sense, there has to be a transfer of energy that occurs when a force makes an object move. You have to make that object move for it to be considered work. And you have to make it move a certain distance. Even if you make it move just a little, you did work, right? So it's kind of like if you're just sitting there and your pencil and your paper, the pencil is just sitting there on your desk and it's not doing anything. Guess what? You are not doing work, right? You have to pick up that pencil, you have to scribble words on your paper, you have to copy down the notes, and now you're doing work, right? But if you're not doing any of that, you are not doing any work. Okay, so you have to make something move in order for you to do work, right? Okay. So picking up a pile of books off the floor, yes, you did work, right? You applied an upward force. You are moving the books up. So if you do that, you are considered to be doing work. So make sure you're copying this on the right side. Just holding the book, a book, if you try doing this, try stretching out your hand, like maybe right in front of you, and just stretch it out as far as you can, and try to get a textbook, and just hold the textbook there in your hand. See if you can keep it there for, I don't know, like 5 minutes, 10 minutes or so on. Like I said, after a while, you're gonna get tired, right? Your muscles are gonna start aching and so on. Feels like you're doing work, but you are technically not doing work, okay? Because unless you're moving the books, I know like if you're holding it up there, yeah, you're gonna move just very, very slightly, but I'm kind of trying to make a point here. So if you are just holding them out there, you're not really doing any work. When I was in kindergarten, I had a teacher that this was back in the 80s, so it was a long time ago. I still remember that she would punish the I guess the kids in my class by she would always punish this one kid. She would have him stretch his hand outward to the side, his right hand out to the side, and his left hand out to the side. And she would make him hold textbooks in his hand. And every time he would drop a book, she would put another book. So it'd get heavier and heavier. And I have no idea why she would do that. Maybe because the kid wasn't doing any work and she was trying to show that he wasn't doing any work I'm just making stuff up. I don't know, to tell you the truth. But it's funny because every time I go through this line, every year that I go over this lesson, I always picture and think of that kid in my kindergarten class. And he was just a kid that wasn't doing his work. So he was doing no work. Therefore, the teacher was making him not do any more work by holding books. But I always think of that kid. I wonder what happened to him. Hope he's doing okay. So how are work and energy related? When work is done, a transfer of energy always occurs. Okay? So here we are with our first formula. To calculate the amount of work done, we're going to use work equals force times distance. So the units for work are joules. So you need energy to do work, right? So it's the same unit, joules. Force, the unit is Newton, and distance, the unit is meter. Okay. So this goes on the right side of your notes, and hopefully you're doing this, just continuing on that section on the right side. And here on the left side, we're gonna jump into our first example, okay? So it says here, you move a 75 kilogram refrigerator 35 meters. How much work was done? So let's plug in numbers, okay? So here, let's do this one first. 35 meters, that goes there, right? Now I want you to notice this one, this number here, we cannot plug this in here or here. Why can't we do that? Well, this is kilograms. And the only stuff that can fit here is if it says joule. So if this is 75J, then yes, you can plug it in right there. Or if it's at 75N, then you can plug it in right there, okay? But now we're faced with, well, what do we do with this number, right? It can't go here or here. So how can we use this number? Well, if you remember, force has its own formula. We went over that already. That force equals mass times acceleration, right? So they are giving us a mass, 75, which goes here. So then what do we use for acceleration? Well, we also learned that gravity can be acceleration. So 75 times 9.8 gives me a force of 735 newtons, okay? So this F gets plugged in right there. 735. 735. And now we're multiplying 735 times 35. And that gives me 25,725 joules. Okay. And again, keep in mind some of these numbers I made up some of these numbers. So I don't know if there's a 75 kilogram refrigerator. I don't know how much a refrigerator weighs, but that's besides the point. I'm just showing you where to plug in the stuff, right? Where to plug in the numbers, and we'll make sense out of what does 25,000 joules mean. You'll see how we relate that to other stuff in another video or in like a lab that we'll do or something like that. Okay, that'll help you understand what the numbers mean. But there you go. Anytime that they give you a mass like this, you might have to revert to using the force formula. So number 2 is a little bit easier. So because they are giving us joules, which goes here, 1800. They're giving us a distance, right? They're giving us a distance which goes here. So we're looking for force. So how do we do that? Well, we divide. 1800 divided by 30 gets me 60. 60 newtons, right? If they give you force and distance on a problem, if they say the force is 2 and the distance is 3, then you would just multiply those two numbers and then that would be it. So you just do exactly what the problem tells you once you plug everything in, okay? So let's move on to power. So this goes on the right side. So power is defined as the amount of work that you can do in a certain amount of time, in seconds. So how fast can you move that thing, okay? Whatever it is that you're moving or you're doing. The faster you can move it, you're considered more powerful. So I know this is a different sense as opposed to, like, let's say weightlifting. You go to the gym and you say, oh, well, how much power can you do? How much can you lift? I can bench press, more than you. I can bench press, I don't know, 300 pounds or whatever, when you can only do 50 pounds or whatever. That's different, okay? That's not really considered power. Power is considered, can you do the same task faster than someone else? Or can that machine do the same thing faster? So if you have two machines, an older machine and a newer machine, and they are both doing the same exact thing, but the newer machine can do it quicker, then that newer machine is considered to be more powerful, okay? And here's the formula. So P, the units are watts, and of course we have work, which is joules, and then we have time, which is in seconds, okay? So on the left side, here is our first example. Let's say it took 5 minutes to move a refrigerator. You did 3,150 joules of work. How much power was needed to move the refrigerator? So let's plug in what we can, okay? So they're giving us 3,150. That's joules, so that goes here in W. 3,150. 5 minutes. Can we plug it in P? Nope, only watts goes there. Can we plug in 5 minutes in T in time? Well, it is a time, but it needs to be in seconds, okay? So let's convert 5 minutes into seconds. There's 60 seconds in a minute times 5 minutes gets us 300 seconds. So that goes here. So 3,150 divided by 300 gives me 10.5. 10.5 watts. And watts, kind of like with your light bulbs, right? You have a 100-watt light bulb, a 60-watt light bulb, and so on. So I know you've heard of the term watts before. Okay, let's do number 2. You move an object 30 meters at a force of 5 newtons. This took a power of 30 watts. Find time. All right, so let's see what we can plug in. So I know 30. I know we can plug that in here in P, right? It's watts. Now I want you to notice, here they're giving us 30 meters. Can we plug in 30 meters here for work? We cannot, because only joules goes there. So if that's it, 30J, then yes, but no, we can't plug it in there. Can we plug it in time? Well, it's not seconds, it's not, 30 meters is not a second, it's a distance, right? So let's hold off on this. It can't go here or here. What about 5 newtons? Can we plug that in here? We can't, because I just said this is joules, right? So, and this is newtons, that's a force that can't go there, and it cannot go here. So now we're faced with, well, what do we do with 30 and what do we do with 5? Because it needs to go somewhere, but it can't go here or here. So, well, if you remember just a couple of minutes ago, we went over the formula for work, which was force times distance, right? So work is joules, force is newtons, distance is meters. So we can plug in 30 here, because it's meters, and 5 here. And we're supposed to multiply these two. 5 times 30, 150 joules, okay? So where does that go? That goes on top. It goes right here, right? That's work, which goes up here. So 150. So we are solving for our time. So how do we solve for time? Well, we're going to cross multiply. So 30t equals 150. We divide by 30. And my time ends up being 150 divided by 30. 150 divided by 30 gives me 5. And our units for time, we said, is seconds. And there we go. That is how we solve for power.